Well, welcome everybody to the inaugural webinar by the IEA Greenhouse Gas Program, IEA GHG as we're more simplistically known. Just for reference, my name is John Gale, I'm the General Manager, and I'm just going to briefly start this process rolling before we bring in Stanley Santos to talk in more depth about the topic of the day. IEA GHG, just for those that aren't familiar with us, is proud to be a member of the IEA's Energy Technology Network. Although we're not directly part of the IEA, we are one of 40 implement agreements that are affiliated to the IEA, and we have a specialist role in advising the IEA and other bodies on the technology options that you can utilize to mitigate greenhouse gas emissions, in particular their costs and their greenhouse gas mitigation potential. We celebrated our 20th anniversary a few years ago, so we're not a new organisation by any means. We are in the process of handing over a number of exciting issues this year. We have a post-combustion capture conference in Canada that we hosted by SaskPower, and they'll provide an opportunity to visit the SaskPower Boundary Dam facility and the Shan test facility. We have the Oxyfuel Net Conference Network meeting coming up in Wuhan in October. You can find the details of both those on our websites. An announcement that we will make shortly, that is in September, that there will be a new special issue of the International Journal of Greenhouse Gas Control, and that celebrates the 10 years of research that has been undertaken on CCS since the special report on CCS was issued in 2005. So it updates the special report, and that'll be coming out in September. We'll keep people more aware on our website. And our other lead activity is the Greenhouse Gas Control Conference Series, and for which we'll also be celebrating next year in Lausanne in Switzerland, our 25th anniversary of that conference series. So that's our sort of forward-looking program, but now what I want to talk a little bit about is the webinar series we're launching. Why now? Essentially, it's a simple answer. Members have wanted us to do them for ages, but we didn't have the IT capabilities of our previous offices. We do now, and hence we're launching this series. The series is intended to illustrate our work, the technical work that the IEA Greenhouse Gas Program undertakes, and we are a technical organisation. We don't advise on policy. We undertake work that influences policy, but we don't actually advise on policy. The first one we have today for you is Stanley Santos is going to share his experiences on industry CCS and the challenges that presents. Stanley has been with the program now for about 10 years. He's got a degree in chemical and mechanical engineering. He's probably better known as one of the world's leading experts on oxy-combustion, but he does think and dream other things at times. And we've had him working on process CCS and process industries. He's managed one study to completion on that sector so far. That's in the steel sector, which he'll refer to today. And the report from that is available on our website. He's currently managing studies on CCS introduction into the oil and refining sectors, looking at CCS applications in the hydrogen production, industrial scale hydrogen production, and a further one on looking at the pulp and paper industries, all of which will be coming out over in the next few years. He's not new to this field in a sense. He was one of the co-lead authors for the European Commission Zero Emissions Platform report that was issued last year on industrial CCS. So at that point, I'll leave it. I'll pass you to Stanley, and I hope you enjoy this inaugural webinar.
Thanks, John, for your kind introduction. Also for the opportunity to present the first webinar presentation for IEA Greenhouse Gas Program. I'm given around 30 minutes to present a complex issue on industrial CCS deployment. I may not be able to present in detail everything within this time frame, but shall provide an overview to different challenges that needs to be understood when working in this area. Also, I would like to mention that we have distributed a list of glossary, and I will re-emphasize this part by part later on in my presentation, and hopefully this glossary will guide you on the different abbreviations that I use in my presentation. I would like to start my presentation with this slide to set the scene why we need an industrial CCS. Okay. This slide comes from the conclusions of IEA publication for the CCS roadmap. One of the couple of key messages here is that CCS is an important component for mitigation. And the second important point here is highlight in the red text here saying that CCS is not about electricity generation alone. We need CCS in industry to be able to achieve the 450 ppm scenario or the 2DS scenario. This slide further reinforces what I have mentioned in my previous slide. This is the recent results presented by the World Energy Outlook Special Report on Climate Change. Referring to the figure to your right shows the same key message to my previous slide, indicating that from 2015 to 2040, a cumulative of 113 gigatons of CO2 should be abated. And to be able to maintain the target for 450 ppm scenario. One third of this cumulative abatement should come from CCS. Half of this should come from industrial sources. In addition to this figure, I should highlight the limitation of the supply side efficiency. Okay? That indicated that a smaller contribution from this efficiency means that CCS is more important than ever to be able to achieve the 2DS or the 450 ppm scenario. Referring to the left figure, clearly shows that CCS in the power generation sector, CCS industrial sector would require a very big share from developing countries, in particular China and India. Without the initiative of China, CCS in industry will not run for sure. We all know that in the steel industry sector, in the cement industry sector, or in the oil refining sector, China is about between 40 to 50 or even 60% of the total capacity in this area. So this slide clearly highlights the important role of CCS in the developing countries. My next slide clearly shows the current statistics where the CO2 emissions from industrial sectors. These slides clearly shows the emissions from the steel industry, about 2.6 gigaton, the cement industry, the fuel conversion, which include the oil refining sector, the natural gas processing industry, the gas to liquid, coal to liquid, chemical, pulp and paper, and other industries. To be able to achieve the 450 ppm scenario by 2050 and beyond, there are currently no alternatives to reach the same level of emission reduction as what CCS could do. There is a limitation to fuel switching, there is a limitation for energy efficiency measures. The lack of CCS would probably lead to other sectors to carry the burden. I would also like to emphasize the contribution by the pulp and paper industry. In this slide, the pulp and paper industry, the CO2 emissions indicated in this slide by the pulp and paper only accounts for the fossil fuel CO2 emission. What's important here is that the pulp and paper industry should be one of the driver for bio-CCS or BECCS. Okay. However, if you survey the pulp and paper industry, why are they against bio-CCS? The very answer to that question is the inconsistency in our policy related to bio-CCS. They perceive bio-CCS as threat to the cost of their raw materials. They have been burned by principles such as in the 1990s, in the UN calculation of their CO2 emissions, their precipitated calcium carbonate is considered a reduction to their CO2 emission. However, in the ETS calculation, the use or the capture of CO2 and the production of precipitated calcium carbonate is not part of their CO2 reduction. So there is an inconsistent policy related to CO2 reductions based on CO2 use in the pulp and paper industry that leads to industry being hesitant to consider bio-CCS in this sector. However, we need to win them over. This is very important for the future of bio-CCS. For example, given the fact that 60% of the current renewable energy right now is from the pulp and paper industry. So this slide shows the different studies that we have done in industrial CCS area. I would like to emphasize that we are very active in undertaking this study, and we have led in various industry stakeholders discussion as well. We faced difficult challenges, and yet we were able to get the respect of the key stakeholders to provide us the right information on how to understand the economics and the technical dynamics of deploying CCS industry. I would like to present some of the key results of the steel industry. Then I will follow this up with some of the overview of the results of the hydrogen production industrial application. This slide only to re-emphasize what we have done for the steel sector. We have completed two reports. One of the report, the techno-economic study, was done together with steel industry in the Scandinavian country. We have contributed around 120,000 pounds to that study. The total cost of that study is £500,000. You can also see in this slide the different lists of glossaries or lists of abbreviations that I use in this presentation. This is an example of an integrated steel mill. This is not the same production steel route that we see in the Emirates Steel, where the first CCS deployment in steel industry will be operational by 2016. So I would like to re-emphasize this type of steel mill is not the same type of steel mill that we will see the first deployment of CCS in the steel in Emirates Steel. What I would like to emphasize here, this type of production route consists of nearly 74% of the production of steel in the world. Okay, this production route consists of the raw material preparation, which consists of the coke plant, the lime kiln, the sinter plant, the iron making facility, which consists of the blast furnaces. There's a steel making facility, which consists of the box shops, and the different finishing mills, which consists of the hot rolling, cold rolling, annealing line, etc. This slide clearly indicated that in an integrated steel mill, it is a multi-point source emission. The numbers indicated in the yellow hexagon shape indicated the percent of carbon that is responsible for the total CO2 emission, while the number in the circle indicates where the CO2 will be emitted. You can clearly see that around 75% of the carbon input to the whole steel mill is going through to the different blast furnaces, while most of the CO2 emissions, particularly the users of the blast furnace gas, will be the point of emissions, for example, in the power plants, which consists of 48% of the total CO2 emission. My next slide shows an overview of the ULCOS program. Okay, this program, ULCOS, is the research program for the European Steel Community to develop breakthrough technologies that could reduce nearly 50% of the CO2 emissions from the steelmaking processes. 3 out of the 4 technologies selected require CCS to achieve such reduction. I would also like to highlight the different programs in Course 50 in Japan and the different program in POSCO RIST, which I have no time to present today. However, I would like to emphasize what are the key learnings that we got while doing the studies for the steel industry. This is a slide showing the the different versions on how a revamped blast furnace would be able to capture the CO2. As you can see, that the top gas from the blast furnace is clean. Most of the top gas will be processed in a CO2 removal or CO2 capture units. Part of the top gas, pretty much between 75 to 85% of the top gas, will be recycled back to the blast furnace. The CO2 removal processes they evaluated in these studies include the use of BSA, BPSA, or a combination of BPSA, PSA, and cryogenic and chemical absorption. What they have evaluated here are three versions. Version 4, which splits the top gas in which inject the top gas in the middle section of the blast furnace and the bottom section of the blast furnace. This version is the version that will be used in Florange demonstrator plant. The version 3 only recycled the top gas at the bottom of the blast furnace, which mimics a conventional blast furnace. This version is intended to be demonstrated at Eisenhudenstadt demonstration plant. However, both demonstration plants didn't proceed, primarily for various reasons, partly economics, partly political, and partly technical. So what I would like to also to emphasize here is that by recycling the top gas, what you could achieve here is between 20 to 25% carbon inputs reduction or carbon savings. This will definitely translate to about 30 to 35% coke consumption reduction. So to demonstrate this concept, I would like to present this slide indicating how the carbon input looks like in a blast furnace. Clearly, clearly, the carbon input into the blast furnace consists of the coke input and the PCI coal input, which pretty much covers nearly 95-97% of the total carbon input. You can, as I mentioned a while ago, nearly 80 to 90% of the total carbon input to the whole steel mill goes through to this process. However, emissions within this process will only coming from the flare of the blast furnace iron making process or from the flue gas of the hot stove. The rest of the carbon will go through as a blast furnace gas or will remain in the liquid steel and eventually will become as a basic oxygen furnace gas. Okay? This is a version, this is a case study where we evaluated the costs of deploying CO2 capture with breakthrough technologies. This is not similar to what ULCOS has evaluated, but this is very similar to the variant of version 1. Okay? In this slide, in this process, we make use of an MDEA 50 solvent to capture CO2 from the top gas. We recycled nearly 80% of the top gas to the blast furnace. And this is pretty much the results of our study. We can clearly see that we will be, once we employ CO2 capture within the steel mill, we will change the profile of the CO2 emissions of the plant. What's important in this slide as well is that from the conventional plant, we have an input of around 448 kilogram per ton of hot metal. However, once we deployed CCS, with top gas recycle, we're, we have reduced the carbon input down to 373 kilogram per ton of hot metal. This is very important. As we have reduced the carbon input to the blast furnace, it also affected, or it also has a very sensitive relation to the coking coal price. Once we reduce the carbon input to the blast furnace, we also reduce the amount of coke needed for the blast furnace, thus making it very sensitive to the CO2 avoidance costs. Once the coking coal price increases, we will also reduces the CO2 avoidance costs of the steel mill with CCS. Please note that this cost only considered the CO2 capture part without considering the transport and the storage. Now, if you will consider the transport and storage, you'll expect additional reduction since you are trying to transport much less CO2 as compared to conventional technology. So I will go to my next couple of slides looking at the second studies related to hydrogen and oil refining sector. We've been doing two studies, concurrently doing two studies. One looking at the cost of CO2 capture in a hydrogen plant connected to industrial complex. And the second one is an oil refinery where we work together with Gasnova, with Concawe, and Sintef. Hydrogen used in industry could be in the form of high purity hydrogen or could be a mixture of hydrogen and carbon monoxide. It is the key raw materials for a lot of processes, mainly for ammonia, for methanol, and also an important ingredient for oil refining sector. What's important to highlight here is by converting hydrogen from fossil fuel, you will also produce significant amount of CO2 as byproducts. This is a simplified schematic flow diagram of an SMR with natural gas as feedstock and fuel. Okay, what you can see here is that once you reform the natural gas, you will go through a shift reactor. After the shift reactor, you have a syngas containing nearly 15 to 16% of hydrogen with 4 to 5% of CO and a slip of 3 to 4% of methane as the main carbon of as the main carbon in the stream. And what you can highlight here is that this gas stream is at 22 to 25 bar in pressure. Once it goes through the PSA, when you recovered a 99 plus percent of hydrogen, you will produce a tail gas, which is nearly about 45 to 50% CO2. This tail gas is used as the main fuel for the reformer, and once you burn this fuel, this will end up in the flue gas that will contain about 19 to 20% CO2. To capture CO2 in a modern SMR, you have three possible options. You have an option to capture CO2 just after the shift reactor. You have an option to capture the CO2 just after the tail gas, and an option to capture CO2 just after the flue gas. For option 1 and 2, typical capture rate will be in the region of about 50 to 60%. For option 3, a capture rate of 90% is possible. However, by replacing this supplementary fuel with hydrogen-rich fuel, you can further slightly increase the capture rate by about 10%. There are several technologies available for capturing CO2 in option 1, option 2, and option 3. For option 1, you can consider chemical absorption, for example, any amine, Benfield processes, etc. For Similarly, you can also capture CO2 by the use of PSA or BPSA or membrane. For option 2, chemical absorption could be used, low pressure adsorbent, even the low temperature CO2 capture is possible. And for option 3, the chemical absorption is probably the only choice unless you have operated a hybrid system. The picture clearly shows here that CO2 capture in an SMR is not new. This is the picture clearly is an SMR in the Wilton plant of Air Products. capture nearly 100% of the CO2 from the syngas of the SMR. I would like to highlight here that the capture of CO2 integrated to transport and storage is right now being demonstrated. We have two large-scale demo plants. These include the Port Arthur project, which is now operational, which captures CO2 from two trains of SMR using BPSA technology. It is important to emphasize that the project to go ahead, you require about $400 million from US DOE as a support. The second large demonstration project is the Quest project in Canada, which is now under construction and probably in commissioning now. Also captures 1 million tons of CO2 from three trains of SMR, and the CO2 captured from this MSR is transported by a pipeline 65 kilometers north of the facility in a saline aquifer. There are two large-scale pilot plants. Exception to the rule here is Air Liquide Port Jerome, where CO2 is captured using new technology or breakthrough technology like the cryocap technology using low temperature process, which utilizes the CO2 for food grade market. On the other hand, the Japan CCS Tomakamai project captures around 200,000 up to 200,000 tons per year of CO2 and injects the CO2 from onshore to offshore. So these are some of the examples of capturing CO2 in an SMR. Okay. So just to give you a conclusion for this section, capture of CO2 from SMR is not new. This is considered a low-hanging fruit, but not cheap. Large-scale demonstration of integrating CO2 capture with transport and storage is now ongoing. This has been achieved. We should expect more of this project. For example, the project in Canada, like the Agrium project and the Sturgeon Refinery project, which will also capture CO2 from hydrogen production plant. Development of new technologies are ongoing. This is aimed to reduce costs. So this is pretty much the summary of what I would like to present about capturing of CO2 from an SMR. So what is how it is important for this technology to be used in other industries like oil refining industry. This is a slide that I've taken from Konkawe. It shows the different percentage of CO2 emissions from the different units within an oil refining. For an FCC refinery, which predominantly produce gasoline, most of the CO2 will come from the fluid catalytic crackers. However, for hydrocracking refineries, which produce more of the diesel, most of the CO2 will come from the hydrogen plant. Okay, what is the relationship of knowing on understanding how CO2 is captured in an SMR in relation to our oil refining sector? This is a slide showing the requirements, the product requirements or product quality requirements for a diesel. It could be noted that in Europe, in North America, we're now required to have a diesel containing only 10 to 15 ppm. Several other countries will still go up to a range of up greater than 2000 ppm. But in the future, we should expect that the demand for a stringent product quality or a lower sulfur content in diesel, in gasoline, in marine fuel, you should expect that with this increasing stringency in the demand of this quality, you should expect a higher demand of hydrogen. And this could be illustrated in the forecast via Konkawe, showing that by having a more stringent product quality, you will require more CO2, more hydrogen, more hydrogen, more hydrogen demand from these refineries, and you can estimate how much more CCS should be required in this sector. My last section of the presentation is regarding the emergence of the carbon CCU. The emergence of CCU is because there is is primarily because driven by the lack of policy that will favor CCS. So development of CCU could provide the development of the emergence of CCU could be a pros and cons of for CCS. Development of CCU could provide early deployment opportunity for new technologies for CO2 capture plant. But in the long term, CCU may not necessarily reduce the CO2 emissions per se. Okay? This is showing an example where these are off gases from the steel mill, where typical off gases from basic oxygen furnaces and coke oven gas are used to produce methanol. What I would like to highlight here is that once we deploy breakthrough technologies for CO2 in the steel industry, it will provide more gas that could be a good raw material to produce chemicals. Okay, this slide shows the different uses of CO2 as a raw materials to the different chemicals. We can see here the urea, the methane, etc. But what I would like to highlight in this presentation here is about the methanol. And I believe the use of CO2 to produce methanol could be the main driver for CCU in the future. As methanol, currently 60% of the demand of methanol comes from our typical products like acetic acid, formaldehyde, silicones, methacrylates, which use these raw materials to produce our daily products like plastics, etc. However, there is a growing demand for the 40% of the methanol, and this growing demand includes the production of methanol, the production of olefins from methanol, and the use of methanol as fuel. And this could lead to a very good avenue for CCU. This is China. Since 2004, they have already established a standard where methanol is used as the direct blend for their gasoline. And in the future, this industry will grow substantially to about 5 to 6% per year until 2025. But what I would like to highlight here is the use of CO2 to produce methanol for fuel could not reduce CO2 per se, and this could be a potential form of technical carbon leakage. This is just transferring the emissions of the CO2 from the production site like steel mill to the user of methanol such as the car or other users. So this is my last slide just to conclude my presentation. Industrial CCS is an important option for CO2 reduction strategy in 2050. There are several challenges in the deployment of CCS in industrial application. Market will define the level of penetration of CCS industry. What we are afraid of is economic CO2 leakage. We need to have a balance or a worldwide policy development for CO2 reduction based on CCU, based on CCS. Early deployment is expected in some industry. I've demonstrated this in Port Arthur project. I've illustrated this in other SMR project. We should expect 2 additional projects in the coming year in Canada. This is pretty much founded with the support of the government, at the same time with a simpler supplier client structure. Now, when dealing with CCS in steel industry or cement industry, where production facility could be moved to another countries where there is no stringent policy on CO2 reduction, will be consisting of the economic CO2 leakage. Okay, and this is something that will become the main barrier of deploying CCS in the industry. Then finally, the use of CO2 as a raw materials is an emerging possibility. This is due to the current policy framework. We should recognize the pros and cons to the CCS. Its pros means that with the emergence of CCU will allow an early demonstration of new technologies. However, in the long term, the CCU alone will not reduce CO2 per se. Thank you very much.
Oh, thanks, Stanley. That was a all-encompassing presentation, very thorough as we'd normally expect. Sean, what do we have in the way of questions? And of course, I now take this opportunity to open the floor to questions for Stanley.
Yeah, thank you very much, everyone. We've received a few questions, but just before we go to those, I would like to remind you of the glossary that Stanley mentioned right at the beginning. If you look at your handouts tab, it's available there to download, just to cover some of the abbreviations that were used during the presentation. Stanley, the first question we received regarding the steel part of the presentation. Did you discover what was actually best for the blast furnace? Would it be ammonia, amine, PSA?
I think they're asking about what's the best capture technology.
I'll rather, there's two things that you need to realize on this question. Okay, the capture of CO2 using breakthrough technology will primarily cover two areas. One is the recycling of the top gas that will lead to an increase in efficiency, which will provide the most of the cost benefits of deploying CO2 capture in the blast furnace. The capture of CO2 from the top gas would consist of either chemical absorption, PSA, BPSA, etc. will now depends on the site condition. If you have excess heat within the site, chemical absorption may be a choice. But if you don't have excess heat, PSA, BPSA cryogenic could be an option. So there is no direct answer to your question. It is important to analyze the cost benefit, which technology is better than others. It depends on the site.
Thank you, and I hope that that's answered that question in full. Next question we had, during the hydrogen section, what capture technology is actually used at Quest?
In the Quest project, the CO2 is captured from 3 trains of SMR. They use a shell adipic technology. The shell adipic technology is based on an MDEA piperazine solvent. Okay, so that is pretty much the technology they use. One thing that should realize here that the arrangement or the configuration of the facility per se, this captures CO2 from the there are 3 absorber columns that capture the CO2 from the different stacks of the flue, from the different syngas stream of the SMR, while there is a common stripper, and they also incorporate a split flow in this technology.
Thank you. Just looking through the rest of them, can you, when you were mentioning CO2 capture from SMRs, you mentioned it as a low-hanging fruit. Are you able to actually quantify not cheap?
Yes. When you would like to quantify what's not cheap, means that if you would like to deploy CCS in the SMR, you will require the process to capture the CO2. Then you will also require additional costs for the transport and the storage. Okay, an example to what I have said about this is a low-hanging fruit but not cheap is, for example, the Port Arthur project, which will require an additional nearly additional $280 million to be able to deploy this technology, to be able to capture the CO2, transport it, and send it to Hastings and they will also require the revenues from the EOR to make it cost neutral. Additionally, in the Quest project, you will require nearly about 860 million Canadian dollar to be able to deploy CO2 capture plus the transport plus the storage in the saline aquifer, and this will also require additional support from the government. And this then the $860 million only covers 10 years of operation. So with this example, I will say that capture of CO2 from an SMR is a low-hanging fruit. Yes, indeed, it is a low-hanging fruit, but it will not be very cheap. Thank you.
Thank you. And I think the final question that we'll have time to take today is, can you expand a little more on the benefits of adding methanol to petrol?
The use of methanol has two possibilities. Okay. In China, when you say M10 to M20, it provides an opportunity to reduce the sulfur content of the gasoline. Therefore, you reduce local pollutions. Okay, that is the direct effect of adding methanol up to, let's say, 10 to 20%. Now, if you're going to add methanol only between 0 to 10%, this will become considered as oxygenates. Okay, when we say oxygenates, this means that this is a octane booster, which only improves the performance of the gasoline to your engine. So these are two perspectives.
Thank you very much, Stanley. And I think that now is a very good time to end. Would like to thank you for your participation in this, our very first webinar. We would certainly welcome any feedback, and we will be in touch shortly with a link to the recording. Should you wish to go over the presentation slides and remind yourself of any parts of the...
I will always welcome any questions and I'll be happy to answer them. Thank you.
Thank you.